All right, folks, so I'm going to go ahead and mix in some of the homework in with a just basic explanation of what we did today. So if we are looking at page 438, 1 through 27 odd, let's go ahead and take a look at number 3 to talk about the first thing that we talked about today. To go over the first thing that we talked about, so we've got 0.9 times 10 to the negative 2. First thing we did today was talk about identification. So scientific notation is the product of two factors where one of the factors is 10 to some integer exponent, 10 to some integer exponent, and the other factor has to follow this very specific rule, must be greater or equal to 1, however, must be less than 10, so it's within that range. So first thing we did was look at identifying scientific notation written incorrectly. And this is, what is this, number 3? And we would label this as written incorrectly. We need to fix it. So this is incorrect because this value here is not between 1 and 10. So we would need to move the decimal place to the right one. So this would be 9. And if we are going to do that, then this must be 10 to the negative 3. All right. So this would be written in correct scientific notation. This would be incorrect scientific notation. All righty. Sound good? So the next thing that we focused on was converting scientific notation into standard notation. So let's go ahead and take a look at number 9. Okay, and this is where we started trying to associate or find some sort of pattern with the number of 0 placeholder values and the exponent in scientific notation. So here we've got 9.3 million, so that's 9,300,000 right here. We're trying to get that into scientific notation. So one of the strategies is to identify the decimal place or the decimal, where the decimal is in the number, and then move 1, 2, 3, 4, 5, 6. So you know we're going to end up with 10 times 10 to the 6th, 9.3 times 10 to the 6th. That is absolutely one way to do it. Or you can, well, you know, actually we're going to talk about zeros here in a second. Well, we can talk about it now. You notice that there are 5 zeros here, so we know we're going to have 5 place value movements, and then one more digit before we get to a single digit to the left of the decimal, which will help us satisfy that A rule of larger than or equal to 1, but less than 10. And so you know what, that's 6 movements without actually having to draw it out. 5 zeros plus one more digits, that's 6 movements to the left. That gives you your exponent, and then you have your A value there. One way of looking at it. Next thing we looked at was going from scientific notation to standard notation. So let's go ahead and take a look at 21. 21 here, we've got 2.74 times 10 to the negative 5. All right, that means we're moving that decimal place over to the left, because a negative exponent above that 10 means we're multiplying by tenths, and that is going to get this number and shrink the heck out of it. So we're going to move our decimal place to the left 5 times. All right, that's going to move us once past the 2, and then we're going to need 4 more placeholders for those 4 additional movements. So one thing we can do is put our place our decimal. We have 4 zeros. And then we have to move past the 2. And that would be our value. All right, we can verify that visually by replacing our decimal place originally where it was, and then counting 5 movements to the left. 1, 2, 3, 4, 5. All right, but we started looking for patterns. And here with negative exponents, we know one of these movements is to move it past this decimal. And the remaining number of movements will give us additional zeros before we have to set that decimal. All right. Finally, we started looking at comparing scientific notation. So let's take a look at, let's say 25. And for 25, we have these different values. 50.1 times 10 to the negative 3, which is not correctly written in scientific notation. Then we have 4.8 times 10 to the negative 1. That is correctly written in scientific notation. Then we have 0.52 times 10 to the negative 3. That is incorrectly written in scientific notation. And then we have 56 times 10 to the negative 2, which again is incorrectly written in scientific notation. So before we can order these, we need to rewrite them correctly. So this is going to take one movement to the right. And in order to do that, we need to compensate for making the a value smaller by making our exponent larger. And not larger in the negative direction, I mean larger in value. So this is going to be 5.01 times 10 to the negative 2. All right, now let's verify that, just to make sure that these are equal. If this is times 10 to the negative 3, I'm going to move this decimal over 3 places. 1, 2, 3, it's going to be 0.0501. If I move the decimal place over to the left 2 times, that's going to be 1, 2, and that will give me again 0.0501. So if I make my a value smaller, I need to make my exponent bigger to compensate if I am trying to fix something that's written incorrectly in scientific notation. Cool. So this is fine. Just go ahead and rewrite that times 10 to the negative 1. We know right away if we're going to order these that this one's smaller. Who cares what the a value is? It's in a totally different place value. Times 10 to the negative 2 is smaller than anything times 10 to the negative 1, as long as this part is written correctly in the same place value, okay? Following the rules of scientific notation. So here, I'm going to make my number bigger by going from 0.52 to 5.2, which means I need to make my exponent smaller. So this is times 10 to the negative 4. Test that out. All right. And then here, I'm going to make this number bigger, smaller, excuse me, by moving the decimal. So I need to make my exponent bigger, which will give me 5.6 times 10 to the negative 1. Yes. Okay. If this is times 10 to the negative 2, I'm going to take my decimal place and move it twice. That gives me 0.56. If this is times 10 to the negative 1, I move my decimal place once. That is again 0.56. This value and this value equal each other. This one is just written in correct scientific notation. So if I am writing these in order, I would then take, let me just do this so I don't get too confusing here. My smallest number is going to be this one. So this is going to be my smallest number. So let's go ahead and let's use a star. So that is my smallest number. This is my next smallest number. All right. Now these two scientific numbers written in scientific notation have the same exponent on the base 10. So that means we're talking about the same place value here. So at this point, we can't tell from the exponent alone which one's smaller or larger. Again, the only reason we can do that here is because it's correctly written in scientific notation, and the place value here is the same. These are both numbers greater than or equal to 1, but less than 10. All right. So now, since we have the same base 10 to the negative 1 exponent, we need to take a look at these values here and decide which is larger. So since this was smallest, next smallest, this would then be our next smallest. And finally, this number here would be our largest. Sound good? So I would want you to rewrite these in the correct order. After you've converted them, then you're going to rewrite them in the correct order. Numbers 23, 25, and 27 might take you a minute. All right, spend the time, do the work, double check, make sure it is correct. You are more than welcome to have communications with each other in Google Classroom on the class comments. If you guys have questions for each other or myself, I'll try to get to it if I can before tomorrow. We'll definitely look at these tomorrow. Have a great evening. Talk to you soon.